Good afternoon, good morning, everybody. I know we've got folks coming in from around the world. Welcome to our VRC webinar for the sponsor series for the CSAT LSAT event, the Action Team series. We're gonna give everybody just a minute to join here, but it looks like we've got everybody coming in pretty well here. So if folks are having any issues joining or hearing audio, please reach out to support@csat.com, support@coldsprayteam.com. We'll be sure to make sure that you get connected to this webinar here. This is the last in our series before we actually have the CSAT and LSAT events here in a couple weeks in good old Worcester, Massachusetts. So we're really excited to tease up the VRC Metal Systems webinar here, talking about all the great things that they're doing, leading up to hopefully some really exciting data and exciting announcements from the VRC team that you'll see at the CSAT and LSAT events. Some of the new technologies, the new materials, the new innovations. And so that's really what we're here to talk about, right, is the next stages of growth in cold spray, in large-scale additive manufacturing. And we're really grateful for VRC's continued support in everything that the Action Team community is trying to do here. And so gentle reminder, and I'll remind you at the end as well, if you haven't already registered for the events, CSAT and LSAT, please do so. We'll share the link here in the chat, and we'll also make sure that you have the email blast as well, so that we can get you guys signed up. That is in a couple weeks here in June, again, Worcester, Massachusetts at the DCU Center. So we'll talk again about that, but in the meantime, I want to introduce Aaron Nardi to the group here. I know many of you have met him before. He's the keynote for our Cold Spray 101 coming up here in a couple weeks. We were just chatting about that and how excited we are about the interest in Cold Spray 101 and cold spray in general. And Aaron has been an instrumental figure in growing cold spray in the cold spray community, both at the R&D level and at the commercial level, with UTRC and RTRC and Army Research Labs, and now as Chief Technology Officer over at VRC Metal Systems. Just a great resource, great colleague. So Aaron, appreciate everything that you and the VRC team have been doing for the community here. And I think with that, we'll kick it over to you if you want to start sharing slides here, and we can get things going. Reminder to everybody, we'll have a Q&A at the end. So there's the Q&A chat down at the bottom of your screen. Go ahead and use that. Queue up all the questions, and we'll be sure that we dive through them with as much time as we have. And there's a few questions that we have kind of pre-submitted, so we'll get through some of those as well. But we're really excited to hear what's coming down the pipeline from the VRC team. So with that, Aaron, the floor is yours, sir. Thank you.
All right. Well, thank you, Aaron. Thanks for that nice introduction. All right. So today I'm going to be talking about a few different things. I usually try to keep my talks fairly technical, and certainly my talk at CSAT will be. But here I thought I'd back up a minute, because I saw a lot of folks on the list who may be new to cold spray. So I wanted to give a brief introduction about just the fundamentals. I'll keep that really short. But then I want to get into a little bit about what VRC is doing these days from a business standpoint, our equipment and so forth. And then I'm going to touch a little bit on how applications typically get selected. And, this is across the wide variety of industries. So I'll give a couple of examples, and then a little bit about cost of cold spray as well in that. And then tied closely to that is qualification procedures at different organizations, as well as, then I can get into the actual applications that have been developed recently. So with that, the cold spray process is a process of taking a gas and running that gas through a nozzle. That gas gets up to a supersonic velocity, and then you get impact on the surface, causing plastic deformation and welding. So the key there, though, the key that you got to remember is it's all about plastic deformation. That's plastic deformation of the substrate you're impacting on, as well as plastic deformation of the particle. So in this process, we use metals. That's predominantly the material of choice. But we also blend different metals together. We blend metals with ceramics. We even do some polymers and polymer blends. So anything that can deform plastically can be cold sprayed. So that's just a differentiator from, other thermal spray processes that, deposit ceramics and stuff like that. That's much more difficult to do with the cold spray process. So the systems typically consist of some sort of control system, usually a gas heater because we say cold, but what we mean is less than the melting point of the material. We have to feed the powder somehow, then we have to mix the powder with the gas, and then it goes through the nozzle. Um, when you do it right, you get a nice dense deposit. This is an example of a nickel. And then when you etch that, you can kind of see that grain and powder structure in the material. It's very heavily deformed, high levels of cold work in the material. And that's really how this process is differentiated from all the other thermal spray processes. It's that solid state nature of the process. So as I said, there's a wide variety of materials that you can process. So we do metals and alloys, we do blends. Metal carbide blends are really popular, especially for wear applications. Bronzes with wear phases or lubricious phases. And then you can create all kinds of structures because you don't have to worry so much about melting and metallurgical incompatibilities and things of that sort. So you can put layered structures together that could be very complex. This is just an example of a three-layer refractory material. All right, so where do we use corrosion? Typically, we do a lot. I mean, the industry by far is dominated by repair and prevention of corrosion, as well as repair and prevention of wear, right? Those are the two areas that are really dominant across a wide, swath of the industry. However, there's a lot of work that's been done in other surface enhancements, whether that be thermal or inductive or conductivity or whatever, antimicrobial even. However, there's also work that's being done in feature addition. So adding features onto an existing part, or actually adding material to make an entire part. So I'm not going to dig into this too much in this talk, but we will have talks at CSAT and LSAT in this area. And really, when we're getting into these additive pieces, there's two ways that we look at it. One is creation of very complex shapes on complex mandrels. And that's a very good use of cold spray. Because it's excellent at putting down thin layers and then building those layers to create, a deposit. You can also, though, use it just like a 3D printer and actually print on a flat plate. And that's being done very widely today as well. All right, VRC, kind of where we fit into things. We started as a company focused on high pressure cold spray. And really the idea was to take high pressure cold spray capability that already existed and scale it to put it into the hands of an operator. So we wanted hand operated high pressure cold spray and also something that could be portable. So that's where the company started. Today we do almost every range of cold spray application from factory use systems to very highly portable systems. We go into the field with systems, and obviously we do work in shop environments as well. See a lot of awards here across multiple communities, different business sizes and so forth. You can also see a variety of customers that we work with across commercial, research, and government sectors. All right, so if we look at the cold spray market as a whole, we can kind of break it down into a few different segments. And these are the areas that we operate is system engineering and manufacturing. That one's kind of straightforward. In order to use a cold spray system, though, you have to have a lot of other stuff. You need gases. You need to be able to collect overspray dust in most places anyways. So you need some sort of sound enclosure, or you need a lot of PPE on the operators to manage sound and things of that sort. So we do integration of our systems with automation and all of these booth configurations. We also do a lot of R&D and applications development for customers. And this is where we're trying to develop specific materials or trying to deposit. You see an example there of titanium being put onto polymer substrates. So, unique applications that haven't been done already, we do those kind of developments for customers too. And then, of course, we sell consumables. So all of this is kind of I would say, the system side, the getting the customer what they need for doing their own cold spray work. We also, though, have a whole services side. And this is, I'll talk a little bit more about this today. The repair services and coding services, as well as point of need services. So if we want to take that process to the field and actually repair really large parts that maybe can't be moved or something like that. And then we also work on operations support. So I'll talk a little bit about that. But first, let me just explain a couple differences in our pieces of equipment. So everything we do is high pressure. It's all high pressure cold spray. So you get that good high velocity, good density, and so forth. But we do put it in different packages. So this package is a very highly portable system. It's meant to be able to go into the hatch of a submarine or some other kind of tight area. You can bring all of the components in by hand. And again, it does the full high temperature and high pressure and temperature application. Now we have our VRC Raptor. So that was the Dragonfly. This is the Raptor. And this is we call it a shipyard portable system, but it's really meant to be either in a factory or in a shipyard where it needs to be rolled around from maybe one location to another. It does have hoist points on the top. It's got a tow bar, so you can tow it around with a vehicle. So it's a portable system, but it's not a hand portable system. It's to be carted around. And again, both of these can be hand operated or robotically operated. They both have a similar temperature and pressure capability. Now we have our factory style system. So I said the Raptor is often used in a factory setting. This is really the system that's meant for factory use, though. It's called our Gen 4. This has a little higher temperature capability, also with the very high pressure capability. And that gets us even higher velocities, which gets you increased plastic deformation, which, if you go back to what I said before, is really the key to cold spray. So now we can deposit a variety of materials with very high quality, super alloys and carbides and all kinds of blends of material. The differences also with this system is that you have water cooling on the nozzle, which does allow you to do a couple of materials that otherwise you couldn't do without fouling the nozzle, of course. And then we also have 2 gas feeders standard with this system. So that means you can put one powder in one powder in the other, and then you can blend the 2 of them together. Now, if you want 3 powders or 4 powders blended together, we can go up to 4 powder feeders in our standard unit, and we can customize to go more than that as well. All right, so Typically, integration solutions include, again, something like a spray booth for your sound enclosure, your robot, maybe a turntable. You need some kind of a spray hood with dust collection. And we also very commonly use nitrogen generation, and we kind of integrate all of these different systems into a facility. Now, if you want to take it a step further, you can have all of that, but also add on things like machining capability that's coupled to your cold spray booth, or you can add in helium recovery if you are going to be doing a lot of helium work. So, I mean, those are all options as well that can be pulled into a manufacturing cell. And then you've got your portable solution. So if you want to integrate for a portable solution that maybe you want to go into a desert environment or into a shipyard, for instance, and you want to have a full capability booth and system, but you don't have a building to put it in or something like that. Well, you can take something like this, and it's a fully enclosed spray booth with its own generator and gas supply. It's got operator space and everything else, and it's all enclosed, and it's got heating and air conditioning and so forth for the operators. So this you can put in at any facility or at any location and have a full cold spray capability at your fingertips. Similar, but in a different form factor, we've got trailer-based systems. So all the same capability, but now put onto a trailer that you can wheel around to a job site. You can pull a cart off that has your robot on it, and then bring that cart over to wherever you're doing your work. All right, so with that, I guess that's kind of our equipment side. Equipment integration and so forth. And all that work is really done, or the bulk of that work is done in our headquarters facility in Box Elder, South Dakota. So we have our systems engineering, systems production, and then some process development and limited production at that facility. We have two facilities close to Worcester where CSAT's going to be. One is with Solvis at their Leominster facility, and the other one is in Webster, Massachusetts. Here we do material research, process research. We do a lot of government work on programs developing cold spray capability and also wire DED capability and things of that sort. And we do some limited production out of those facilities. We have full production facilities in both Chesapeake, Virginia, and San Diego. I'll talk a little bit more about those. And then we have two subsidiaries who also do cold spray in a production environment. And that's Mid-America Aerotech and Heartland Repair and Coatings. And I'll talk a little bit about them as well. So first, the production facilities in San Diego and Virginia. Here, we've got both facilities certified to be able to do qualified spray procedure development for the Navy. So these were primarily focused on Navy activities. However, they also do a lot of work for other DoD and commercial sector industries as well. So they have a lot of capability. They're full spray booth, qualification, lab, machining capability, mills and lathes and so forth. And then they also have equipment that can be taken portable and go out and do field services locally too. So we can lead off of those facilities and do in the field repairs. Mid-America Aerotech, this is in North Dakota. They have a full service MRO capability. So they do everything from machining and inspection. They do testing of all kinds, hydraulic, pneumatic, and so forth. But uniquely, they also do a lot of cold spray development, and they implement cold spray repairs into their MRO process. They're also doing work with electrospark deposition, also in service of their MRO clients. They have their full certifications to be able to do FAA work and Europe with repairs in Europe as well. All right, now Heartland Repair and Coatings, they do a little bit different work. They focus more on the oil and gas sector and some of the heavy industrial sector. And you can see here they do a lot of work with pressure vessel fabrication, structural fabrication of skids and pipe stands and so forth. And they'll also do custom process piping for installations. Now, where cold spray fits in with them is they've actually developed a patented process for repairing gas pipelines and oil pipelines and so forth that have been eroded and worn over the years. Well, they can go back in and add cold spray material to fill in the wear and then apply a composite wrap to certify that pipeline. Now, they also do work with other pipe and vessel coatings for corrosion, wear, and so forth. All right, so you've seen there's a lot of production capacity, production capability, but there's still a lot of reasons why we might need to bring capability into your own four walls. So, one thing I like to stress is that cold spray is really easy to do. It's difficult to do well, though. And for those of us who have been in the industry for a while, things can pop up and you learn a lot about masking and robotics and all the extra things around cold spray that actually make it much more complicated and, to get it just right. So to help people out, we do a lot of support training people. We do a variety of different training, whether it be kind of extended period training, like maybe 2-3 weeks or so. But we also do things like where we'll stagger the training. We'll come out, do the initial training, then go away, let the folks work with the equipment and try to work out some problems, and then come back and do more training. And that's helped quite a bit, in getting people kind of up to speed on how to use the systems and the equipment. Also very important to do calibrations regularly. We have an annual calibration schedule we work out with most of our customers to try to certify all the sensors that are in the system and verify that everything is running the way it should be. You can go a step further, and we have a full PM of systems. So we'll actually go out on a periodic basis, usually once a quarter or something like that, and do full PM on the systems, replacing anything that needs to be replaced and so forth. And with that, we also give reach back application support. So this is where customer has a problem, they have identified an application or a potential application, but they just don't know the right material or the right way to develop the masking or whatever, and we'll work with them and develop that application with them so they can go and generate that ROI that they're looking for. And then access to prototype hardware and so forth is a big benefit with that as well. And then kind of at the full extreme end is we also put people on site at customers' facilities. So you kind of get all of that PM application support, and you also get a person on site every day working hand in glove with the folks at the facility to develop those applications. All right, so I'm going to change gears now and talk about application selection. So a lot of industries classify things differently, but these are a few categories that several of the industries tend to use, including whether it's a structural application, a critical application, if it's got corrosion concerns or wear concerns or whatever. And this classification typically defines what kind of testing is required. And a lot of times that's embedded in some sort of a process specification. So if it's a commercial industry, it could be a material spec or a process spec that they have internally. The Navy uses something called the UIPI. I'll talk a little bit about that, or so forth. Now we get to the material selection piece of it, and there's a lot of factors that might go into that material selection, mechanical requirements, physical requirements, and so forth. But also down the list sometimes is material cost. It does become pretty important, you'll see in some applications, or even just customer preference. Some customers are used to certain alloys, certain systems, and they want to use those for their repair. Now, as you go through the qualification process, I'll talk a little bit more about that, but there's necessarily a lot of testing that gets done when you're qualifying an application. And one thing that's important to consider when you're setting up specifications and process plans and so forth is having a mechanism that allows for altered processes. So there's not many places that do this, but having a primary path for qualifying and a primary group of tests that need to get done to qualify an application, but then some subset of testing for requalification if you want to change something small. Like say you decide I'm going to go from this geometry to this geometry. Now I got to change my robot speed. Well, all of a sudden, if your process was qualified with 200 millimeters per second and you want to go to 100, now you got to requalify everything. That gets to be very difficult. And changing feed rates is another one, and I'll show you an example of that. Or even upgrading to a new model of system, right? A new cold spray system or something like that. How do you prove that what you're doing here is the same as what you're doing there without going through a full requalification? All right, so a lot of times what we talk about when we're trying to select an application is, especially if you're new to cold spray, is where's the low-hanging fruit? What is that thing that's going to be easy to get, easy to implement, easy to qualify, and also give me a big ROI? Well, one of the first areas that people look at is high cost parts. And this is, I'm showing aerospace examples, but this could be any industry. High cost parts that are non-structural, cosmetic, or maybe functional. Maybe they have a wear aspect to them, or they're a sealing surface or something like that. These are typically what people look at as lower hanging fruit because they may not have as many testing requirements. The other area, though, that gets you a fast ROI and can be a fairly low-hanging fruit is a non-structural, cosmetic, functional type of repair, not on necessarily a high-cost part, although what I'm showing here, most of these probably are high-cost parts, but it could be just a high cost to remove it from service or to transport it or something else. So the first two examples you see here are examples from some of the Navy work that NAVC, Penn State, and in some cases VRC worked on collaboratively. You see the third example I'll actually talk about a little bit later. Is a example that we just did recently, and then the last one is just a picture of a bridge. So if you have something you can't move, right? How do you repair it without completely cutting it and taking it out and replacing it? After this, we start to get into costs and what kind of cost benefit you get out of a particular application. And then finally structural and so forth. So this is the most difficult application typically because it does require a lot of testing. So let's talk about cost for a second. If we look at your basic cold spray process, we can break down the major costs of any process into these three categories: labor, materials, and logistics. So there are other important factors like capital cost and routine maintenance and all that kind of stuff. But really the bulk of the costs on a part-by-part basis fall into those first three categories. So if we focus on those for a minute, with your labor costs, you have things like the how many parts are you doing at once. So this is obviously you do a 1-part lot versus a 10-part lot versus a 100-part lot. There's a big difference in your setup costs, your fixturing costs, and all that kind of stuff. Is the geometry simple? Is there a lot of automation? What's the masking like? Are you repairing it at the point of need, or are you repairing it in a factory? All these things kind of play a role in the labor costs. Material costs come down to the actual cost of the material, the DE of the material, and then how big is your area that you're repairing. Of course, there's the gas. Now, if you're doing helium, that's obviously an important factor. Nitrogen, a little less important of a factor. And then there's logistics costs, shipping parts, shipping people to the parts, all that kind of stuff. So let's look at a simple case study. If we take a high value magnesium part, let's just say this is a part that's got a surface that's 24 inches in diameter, and it's got about a half an inch height, and we want to put 50 thousandths of an inch of material down. And let's just say, as an example, this part costs $100,000. I've got the cost of helium, nitrogen, a helium sprayed powder, aluminum powder, a nitrogen sprayed aluminum powder, and then the relative DEs of each of those. So all those assumptions are here. So we start to look at what the most basic cost would be. So this is, I'm not even getting into profit margins or anything like that. This is just your base cost. So your real costs are even higher than this. But if we just look at that base cost, you've got about $4,000 to repair this part. That's using pretty typical numbers for how you would spray a helium sprayed version of this part. This is a standard helium process of 6061, spraying 6061. So that's still only 4% of the cost of the part. So it's still a big value to the customer to repair that, but it is $4,000 to repair that part. If you did some modifications to that process, and this is where it becomes important to have that mechanism to be able to change your process around, because if you do, you can increase your feed rate, increase your velocity so that you still get the same thickness per pass. And now you're getting down to about 6 minutes of spray time instead of 30 minutes. And all of a sudden your per part cost goes down to $700, $800, right? But that also includes more parts in a lot, right? I assumed a 10-part lot here as opposed to a 1-part lot for the first case. So basically increasing the powder feed rate and then increasing the number of parts you spray gets you to this significantly lower cost. Now you can go a step further and go to nitrogen, but now your increment is much smaller, right? You're going from $800 to $400. It's still an improvement, and it could be very important, especially if there's difficult logistics in getting helium, right? But the difference between the first two is a much bigger factor. All right, now we'll do kind of a little bit different of a thing, right? This is a steel part where we have kind of a large surface that's going to be coated. So we're going to be putting down quite a bit of material. I've got a thickness of about 100 thousandths of an inch defined here, length of 14 inches, diameter of 12 inches. A lot of assumptions down below. I won't read them all off. And now, if you start to look at a helium repair, with this material, this is CrCO1. It's a chrome carbide nickel material. It's used very commonly to repair steel parts like this. Even with a pretty high stream loading, not incredibly high, but a pretty high stream loading, it's still going to take 7 hours to put that material down. So your cost of doing this job with helium would almost be as much as the whole part cost. So you really can't do that. But if you now switch over to nitrogen, even I'm assuming only one part here, still one part lot, you bring that total cost down to about 12,000, and now you see the large bulk of that cost is now in your powder, right? So the green is your gas in that little pie chart. The green is your gas, the red is your powder, the blue is your labor. You can see, well, the bulk of it is now the powder. If you go a step further and select a powder that's a lower cost material, right? Now you can bring that cost down even further to just under $4,000. And now you've got kind of an even distribution of your gas, your labor, and your powder costs. So that's really just a couple examples of how different assumptions and different paths to a solution can make really large differences in the cost of a job. All right, I'm going to jump over to qualification procedures, and the first one I'm going to focus on is NAVC. They've done a really good job of creating this UIPI system, which allows them to, at the shipyard level, qualify their own repairs across platforms. So basically, across the ships that they service, they're able to use this UIPI to dictate whether they can do a repair or not and how to qualify that. So as long as you stay within these guardrails of what this UIPI allows, you're able to qualify your own repairs locally. This is kind of unique amongst the DoD because it's got that cross-platform capability, I guess. So the way this works, like everybody else, you qualify like what that category of part is, whether it's structural, wear, corrosion, whatever. You identify the tests you're going to do. You pull up the ASTM standards. You run it per the standard or per the UIPI itself, depending on the test you're running. And then when you're done, you all that data goes back to the shipyard. They sign it off, and this QSP goes into the appendix of the QSP of the UIPI. So it's a pretty straightforward process. We've done it a bunch of times with our repair sites, with our production sites. Works quite well. They just released recently a tech pub. Now, this is a similar document to the UIPI, but it actually allows a similar application of the technology at the commercial shipyards, as long as they're doing Navy work at those commercial shipyards. So they have this process to allow them to do that there. Next, I'll just talk quickly about DoD aerospace. Really, a lot of what you're going to see from here on is that every platform and every part needs to be approved, right? They're even non-structural, non-critical, all those applications require approval part by part, pretty much across the board, with a few exceptions. And this includes the program offices as well as airworthiness. They may reside at different locations, but all these folks typically need to sign off on every repair. The Air Force is a little unique. At the wing level, they actually also require every single part, every single not just part number, but serial number to be signed off, because they're also trying to maintain traceability of which parts have been repaired and which parts haven't, right? At the depot level, it's a little broader because they have all the paperwork in place there for the repair of the part. So they're allowed to execute that repair on that part number whenever needed. At the Army, they have a slight exception as well. They have certain cases where they have blanket approvals for certain categories of parts. So magnesium repair is one of those for non-structural applications. And that got a lot of MEOs issued early on the Army side. Structural repairs, like I said before, are pretty rare still. There's a few out there, but they require a lot of detailed testing typically, and sometimes full component level testing, and that gets very difficult to do. So there's not as many of those around. Interestingly, the Air Force can execute repairs on any other ground vehicles with just the local TPOC signing off on it. So that's kind of an interesting carve out on the Air Force side. There's really no mechanism in place for cross-platform approval authority. So like the UIPI that the Navy has, there's not really that same mechanism that allows that local approval for a category of of parts, with that Army exception, of course. All right, Army ground-based systems. This is really, I don't want to say ad hoc, but it's a little different when you go from one PM to another PM because of the way that different platforms operate. But it is still a part by part and a platform by platform approval. Some PMs really rely more on the OEM to do the approval, and some do more of a local approval or a Army approval for that. And there are some efforts in place to try to get cross-platform approvals, at least at the individual depot level. So a particular depot might be able to get approvals to do a category of repairs. There's not really a mechanism in place, though, still for cross-platform and Army-wide approval authority there. Now, commercial aerospace, I mean, it's pretty straightforward. They have processes in place. The OEMs have repairs that they implement all the time. They have to go to the FAA or the DoD to get those approved, but those are very robust processes. They do them all the time for a wide variety of repairs. And those approvals are pretty straightforward because the OEM is typically the design authority for those. Coating replacements are typically minor repairs, form, fit, function. Organizations like MROs, for instance, can do those types of minor repairs just with an FAA repair station certificate. Major repairs, though, still have to either go back to the OEM or get DER approvals. And then I guess the last one I wanted to focus on is other kind of commercial industries. They vary quite a bit, I should say. But the nuclear industry, they may be risk averse, but they do have a lot of applications. Corrosion and material composition are typically what they care about. Oil and gas, heavy industry, they're usually performance-based, and a wide variety of other industries really define what they need to qualify, sometimes based on what the cold spray service provider suggests. So having those internal processes at the service provider level is really important to meet those customer needs. So last thing I want to talk about is just a couple of applications. This is an application we've been doing for many years now. It's a crevice corrosion problem. And here we have a very corrosion resistant substrate, but we're adding an even more corrosion resistant coating because they do have this crevice problem at the flange. This is what it looks like. They have these corrosion pits that form at defects in the casting. We've looked at titanium and nickel-based solutions and have done a wide variety of corrosion testing. And really, it comes down to titanium being a very good corrosion-resistant material for these applications. So titanium is really the gold standard here in these crevice applications, and that's what we've done. We've developed the whole process around this, and as I said, we've been doing these since about 2020. We've done quite a few, and we've even done them just a month ago or so. This is a new application. I did talk about it last year, but it's still a new developing application for a wear-resistant coating. This is an abrasion-resistant coating. So we've developed this stainless steel-based material that's a very good wear-resistant material. Did a bunch of wear testing of deposition efficiency to try to figure out costing of this process, and we're working with the company now, Hutchinson, to bring this application further. This is a part I showed on a slide previously. This was actually done in a factory environment, but it was done, it's a very large part, so it really couldn't be moved, which is why we had to go into the field to actually do this repair. We did it in collaboration with NAVC and Penn State, and put down quite a bit of material, 126 kilograms of material over 28 hours, so a lot of material on this part. But it saved a ton of time in dry dock for this ship. This was an application that NAVC and Penn State did with our equipment in a submarine environment. So this was actually inside of a submarine, small part, but to disassemble this part and remove it from the sub was going to take a lot of time. Again, lots of dry dock time, about 5 months they estimated. So being able to repair this in service was a huge win for them. And this is a part we did just recently. So this is a hydropower application. This is like the largest ball valve on the East Coast. It's gigantic. And obviously removing this thing from service was going to be very difficult, but moving it, physically moving it and being able to bring it to another location was just out of the question. So we brought our equipment to a facility where we were able to set up a makeshift area to actually do this coating. Before the coating, here's an image of the surface. You could see here we set up a little temporary spray room where we did the work. Obviously, we have all of our dust collection, we have our cold spray system and so forth. Inside of that, we have a manipulator to rotate this big ring. We were able to spray a coating on the inside of this ring and build up little over 1/8 of an inch. So, and then they were, of course, able to go back and machine that and finish it up. So with that, hope I didn't go too far over my time here, but happy to answer any questions that popped up during the talk.
Awesome. Thank you, Aaron. You covered like all of my favorite things in cold spray, including a lot of the key points that so often we miss, which is, really about like those decision criteria and like where we can really use cold spray and how we can think about it. And so I'm curious, as you think about, maybe the customer journey in some of these applications, where do you find some of the best ways to actually help folks see what those opportunities are? Like, how do they really work with you guys to get from this idea phase to here's a real application that we can add real value for the customers? What's that journey like for you guys, and how do you bring folks on that journey with you?
Sure. So it's pretty rare that a customer, especially a customer new to cold spray, is able to come in and have a fully formulated idea of what they want to do, kind of put it on the table and have us just quote it and, do the work, right? That's pretty rare. Most of the time, we, first get on the phone with the customer. We're going to talk through like, what is the problem? What are you really trying to solve? They might have an idea of what they want to do, but after discussions, we say, hey, there's a few different ways you could attack this. And if you could have a little allowance here or there, we might not need extra masking. We might not need, special equipment. We might be able to get into this area easier and so forth. And of course, my background is heavy in materials, so I always like to kind of focus on that side and try to figure out what I can do with a particular material that'll make their life easier or give them longer life or whatever. So usually those are the discussions we have kind of up front and set the stage for, is this an application where cost is not as big of a factor, like it's such a high cost problem that they need, the solution that is the absolute best solution, or is cost a major factor, in which case we'll start to play games with, well, can we back off on this requirement a little bit, this wear requirement or something else, so that we can use this lower cost material, or can we back off from the use of helium or something and start to use a nitrogen solution, things like that.
Got it. That's kind of a good segue into the next question that we have, which is around some of the other processes that are out there today for things like repair and coating. So thinking about especially like maybe hydraulic cylinder applications and other kind of wearing surfaces, maybe where do we see the balance of like cold spray versus laser cladding, classic thermal spray? Where do you see the kind of those decision criteria points being?
Yeah, so that's an interesting question because most of my career in cold spray, anyways, I've kind of been trying to focus on where these other processes really couldn't go, right? So there's a lot of things that thermal spray can't do, but you'd like to use thermal spray for. So those are the kind of a lot of the areas we started targeting. Um, However, there are some folks who want to actually just use the cold spray for something that they could have used HVOF for or something else. It's always a interesting kind of decision and logic tree that you have to go through with the customer to say, is this the best solution or should you be looking at something else? Because I don't want to, it's not good for us to go down a path to try to force cold spray into a box that it doesn't belong in. If you've already got HVOF, you've already got the capability, it's easy to do with HVOF, maybe don't go the cold spray route unless you have something you're not attacking, right? So like bond strength's a big one. So HVOF, maybe you can't hit the same bond strength as you can with cold spray. Maybe you don't have the same impact resistance. Maybe you don't have the same fatigue resistance or something like that. And hey, I really need that little extra fatigue performance or whatever. Well, then that makes sense, right? We'll go down the cold spray route. Um, Now, on the other side, the other, I guess, case is welding, right? So cold spray is not a substitute for welding, right? And I try to emphasize that with people quite a bit because there's been a lot of people, and we've done it many times where we've tried to weld two parts together with cold spray, and it works. It can work. There are some reasons you might want to do that, but it's pretty rare. So, welding is pretty well established. If you're joining two pieces of material, that might be the better solution for you. However, if you're using welding because that's all you have and you're trying to fill in an area on a part with a weld bead, and now your part turns into a potato chip, well, maybe that's the good area for cold spray to be used, right? So I don't
Yeah,
know if that answers your question.
I think it does. I think it does. I think that balance of what are you actually trying to accomplish? Where is the existing process capable, and what are really some of the underlying physics, right? The heat inputs and things like that. Really, I think that's the driving factor that you're talking about. There's a bit of a different direction here that I think some of the questions want to go, which is towards some of the new capabilities that you touched on a little bit in your slides, especially with the Gen 4, and thinking about, what is it really capable of, and maybe a little bit on where you see kind of use cases for the graded material combinations that you can do with the Gen 4, and really what does that open up as far as the future of cold spray?
Yeah, so with the with kind of that material grading, there's a couple things you can do. One, if you were trying to create a mechanical alloy and then do maybe post-process diffusion treatments on that material, where you then create that alloy in solid state. So say as an example, you kind of mixed a little bit of titanium and nickel together, right? And you sprayed those at different concentrations. Well, now you can post-process and get a graded nitinol block of material, right? There may be applications for that. There's also applications for going from like a higher hardness material or maybe a more ductile material, to another, right? So say I wanted to have say I got a steel part and I want to have a tough layer that I put down first, and then I wanted to go to a very hard coating at the top, but I didn't want to have a defined line. I wanted to kind of grade into that high coating. Well, I can go with maybe a nickel first, and then I can slowly grade in a tungsten carbide or something like that. And then I get into my full tungsten carbide layer at the top. Now I don't have that distinct line in the middle where now you have a risk of an interface and things like that, right? So those are areas where that kind of has played a big role.
Got it. And kind of continuing on that Gen 4 theme, and we'll try to sneak a couple more questions in here before the 5 o'clock hour. Yeah. What are some of the innovations that you guys have worked on to help avoid nozzle fouling, and where do you still see challenges with nozzle fouling, particularly with some of the innovations that you guys are working on today?
Yeah, so nozzle fouling has been a major issue. With the new nozzle materials we have a ceramic nozzle that we're using, as well as some metallic nozzles that we're using. With that combined with the water cooling, we can get to much higher spray temperatures without fouling, with some of those materials that tend to be prone to fouling, like stainless steels and Inconels and things like that. Titanium sprays pretty well regardless. Like CP titanium sprays pretty well with anything. Funny one is Ti-64. That material, when you're spraying it with helium specifically, it tends to foul. But you could spray it with nitrogen, no problem. And we do that all day long on the Gen 4 or even our other systems. So it's one of those unique materials. That problem, I wouldn't say we've solved that one yet, trying to spray helium Ti-64 specifically, but I think we've made a lot of progress on all those other materials, being able to spray those at much higher conditions.
Awesome. That's fabulous. So we snuck that last question in. Well done. So that brings us right up to our time here for the VRC sponsor webinar series here with the CSAT LSAT event. I know there's still a bunch of remaining questions in the background here, so we will share those with the VRC team and folks who submitted those questions. Definitely recommend that you reach out to Aaron Nardi and the team. They are incredibly helpful, incredibly knowledgeable, all things cold spray, from the applications, the materials, obviously the machines, and everything in between. So please do reach out. And also be sure to register. You can see the QR code down in the bottom right corner of your screen. The CSAT LSAT events, June 11, 12, and 13, just up the street from here at the DCU Center in Worcester. Everything is already filling up. So if you haven't registered for the receptions, one of which will be at our Leominster facility, where VRC, Speed 3D, and EWI are all co-located. We all have booths set up. You'll see real cold spray, you'll see real WAN, you'll see real friction stir additive. Come check that out, as well as the reception following the LSET event. Those are both filling up very quickly, so definitely recommend registering for those. If you have any issues with registration, reach out, call us. We're here to help. And I think with that, again, thank you to the whole VRC team for continuing to be a good, wonderful supporting partner in this growing community. And to everybody that joined us this afternoon, this evening, this morning, thanks for being part of this community as well and helping to grow the ecosystem that we're building here to keep solving bigger and bigger problems in cold spray and large additive. So thank you all very much. Appreciate the time and effort this afternoon, and we'll see you all in a couple weeks.
All right. Thanks, Aaron.